On today's video, we're just going to work the two hard problems, so 4 and 5 on this list, from last time's classwork. That way everyone will know how to do it no matter what. So we're going to start with number 4 about the cannon. So here we are. It says a cannon launches a cannonball, at 25.15 degrees with an initial velocity of 10.43 meters per second. How long is the cannonball in the air, assuming that it lands at the same elevation from which it was launched? Now, if you're in one of my AP classes, you'll notice that this part, assuming that it lands at the same elevation for which it was launched, has been added. It really should have been in there to begin with, but that should help a little bit in setting up the problem. So let's start by drawing a picture. So cannon launches cannonball at 25.15 degrees. So we got a cannon. Here's our cannon. And it launches a cannonball at, what do we have, 10.43 meters per second. And it makes an angle with the horizontal. And that angle is 25.15 degrees. Okay? So that's what we have. And then we say that the cannonball, this is apparently a cannon like buried under the ground or something. The cannonball lands over here somewhere after a more or less elliptical flight. Something like this. Okay? So, we have a VI. Well, we have a VI. We do have a VI. VI is 10.43 meters per second. Now, since this is a two-dimensional problem, we're going to have a VIX. We're going to have a VIY. We're going to have, we could possibly have a VFX. We could possibly have a VFY. We could have an AX. We could have an AY. And we can have a delta X and a delta Y. And we can also have just delta T. And delta T is constant. It doesn't have a direction because it's just time. So here are all of our possible variables here. Let's see which ones we know. Well, we assume the acceleration in the x direction is 0. We've talked about that, how we assume that the initial velocity and the final velocity in the x direction are going to be the same. This just makes things simpler, and we're ignoring air resistance, that sort of thing. So there's that. We know the acceleration in the y direction. It's negative 9.8 meters per second squared. We know the displacement in the y direction. The displacement in the y direction is 0. How do we know that? Because it says it lands at the same elevation from which it was launched. So that means we did not move up and down. Okay, what do we want? We just want time, right? How long is it in the air? Yeah, we just want time. So that's not so bad. So we need to figure out either VI or VF, or possibly both. So what do we have here? We've got 10.43 meters per second at 25.15 degrees. So what we can do is we can find the x and the y component of this. So there's the x component, there's the y component. This would be VIX. This will be VIY. Now remember, finding components is really easy. VIX is just going to equal 10.43, cosine of 25.15, and VIY is going to be 10.43 sine of 25.15. So we can figure those out. So we get VIX is 9.4412. I'm going to fill that in. And we know this is meters per second. And VIY is 4.4326. Okay, so we filled that in. Now, what we really just want is time. So if we look at our knowns in the y direction, we'll see that we've got VI, we've got A, we've got delta Y, looking for T. So in a perfect world, we would just now say, okay, well, delta Y equals VI T plus 1/2 AT squared, and just solve this for T. Except that solving this for T is kind of a problem when VI isn't 0, and VI isn't 0 in the y direction. So we can't do this, by the way. It should be VIY, it should be AY, you know. In the past, we were kind of lazy and we didn't put our subscripts, but now that we could conceivably have a VIX instead, or an AX instead, we need to put our subscripts on these. So this won't work. We can't use that equation. So that must mean that we're going to need to find VF. So let's find VF. How can we find VF? Quite easily. VF squared equals VI squared plus 2A delta Y. Okay, this is AY, this is VIY, this is VFY. So solve this for VF Y. That's just the square root of VIY squared plus 2AY delta Y. Notice when we plug in, let me actually plug in. VIY is our 4.4326, that's squared, plus 2 times negative 9.8 times 0. Okay, 2 times negative 9.8 times 0 is 0, so we can ignore this. We don't care about that. So now we just get the square root of 4.4326 squared. Now I saw way too many of you yesterday trying to punch this in your calculator. What's the square root of something squared? That thing. The square root of 3 squared is 3. The square root of happy face squared is happy face. Okay, it doesn't matter. So the square root of this is just 4.4326. And now a lot of you were looking at this and being like, huh, that doesn't make any sense. And you're right, it doesn't. Remember, the square root of 3, or excuse me, the square root of 9 is not 3. It's plus or minus 3. So this is a velocity down, right? Don't we expect our cannonball to go up and then back down? Yes, of course we do. So our VF in the y direction is negative 4.4326 meters per second. This is something that you should just know. So write this down somewhere in your notes. When you have an object in projectile motion and it lands at the same elevation that it leaves, that is to say delta y is 0, your final velocity is the negative of your initial velocity. Every time. Whenever the displacement in the y direction is 0, for projectile motion with gravity involved, the final velocity is the negative of your initial velocity. Every time. Remember that. Alright, so we move this crap out of the way. So, now we can just find t using pretty much any equation we want. Let's do a good one. Let's use the easiest one. VF equals VI plus AT. I'm going to rearrange this for t. So I'm going to get t equals VF minus VI over A. Got to be really careful with your signs here. Notice that VF is negative. So negative 4.4326 minus 4.4326. This difference is not 0 over negative 9.8. And so that ends up being 0.9046. seconds should be our delta t. Let's see if I got it right. I haven't actually checked this. Let's see if that's the correct answer. Is it 0.9046? Moment of truth. Yay, I got it right. That's not rigged. I just worked it and got it. Okay? So that's how you do that one. You know, if you're really lucky, there's a 1% chance that these are the two numbers that you got. So that'd be nice if that happened to you. So that's number 4. It's not so bad. Now I'll do number 5. And number 5 is a little tougher. So here's our egg catapult question, and the sharp-eyed viewers among you will notice that I've retconned this in the same way I retconned the previous one. We're saying the egg hits the ground at the same elevation from which it was launched. Just because that's what was implied, but the implication wasn't really getting through. And it was kind of vague, so I apologize for that, but I fixed it, so no worries. Let's just jump right in and draw our picture. So same kind of deal. Let's start with some ground, and then we launch an egg, and you know, we think that it's going to probably do something like this. You know, we don't know how steep that's going to be necessarily or anything. So that's our picture. I'm going to draw a sub picture down here. We actually don't know this velocity. This is actually what we're looking for. The initial velocity of the egg. This is the initial velocity of the egg. We do know the angle. They gave us that on this one at 60.02. And we know delta t. We know delta y is 0. We know ay is -9.8. And that's all we know. All right then. So this problem kind of seems impossible the first time you read it, because if these are the only knowns that you can find, you know, you get some really strange looking results. Here's the key. What we want to do is find VIY. If we can find VIY, we can just do trig and find VI, which is our answer. Alright, so we want to find VIY. So I'm going to write that down as our unknown for now. We want VIY. So this isn't actually that bad. I helped a few of you yesterday or the day before, last class, one way or the other, do this in a way that was probably a little tougher than it needed to be. We can just use this formula. Delta y equals VIY delta t plus 1/2 ay delta t squared. That's our 3 knowns and our 1 unknown. And we can solve for this. This isn't a big deal. So rearranging this, we get VIY equals delta y minus 1/2 ay delta t squared divided by delta t. Alright, so that's not so bad. Just plug in 0 minus 1/2 times -9.8 times 12.97 squared divided by 12.97 equals 63.553. So VIY is just 63.553. So that's this vector, this component anyway. Alright, so now we can just do trig to find the rest. We have to find the hypotenuse, and that's what we're looking for. So it's opposite this hypotenuse, so what sine of 60.02 equals opposite 63.553 over hypotenuse VI. So VI equals 63.553 divided by sine of 60.02. So that is, I got 73.3699 meters per second. And again, let's check. I haven't made sure this is right. I might have just missed it, like the rest of you may have just missed it. What was it? 73.3699. Okay, 73.3699. Moment of truth. And there we go. I'm actually really relieved. So there we go. That wasn't so bad. You just have to keep your bearings, trust your kinematics equations, and do it. The rest of these are a whole lot more similar to the examples that I worked in the previous video. I'll talk about each a little bit. The ball rolling off a cliff. I don't know how far away from the base of the cliff the ball lands. You just find t in the y direction, and then use this velocity times t to find the displacement in the x direction. That's pretty easy. It's exactly the same, actually, with number 2 and number 1. It's exactly the same problem. Hey, and number 3 also. So all three of these work exactly the same. You just, have different numbers. The words are different, but all three of these are really exactly the same problem. So I'm going to have you a few more questions to work today. Not really adding any new content, just going to give you some more practice on these because I think most of you can use it.